Hello. In this video, let's look at another model that helps us understand drive current in scaled MOSFETs. So as we've seen, the basic model of the MOSFET is the square law model, which was developed in the 1970s, and it's a great instructional tool. So we use it almost by default in almost any of our digital designs. Now, when we discussed the model, we also looked at the fact that as MOSFET scale or as the electric fields in the MOSFETs increase, the assumption of the gradual channel approximation actually fails. And this is very true when the transistor is biased at high drain fields. So in such situations, we use something which is known as a velocity saturation model. This is again by no means predictive to what's happening in technology today, but it's slightly a step up from the old model and gives you some additional intuitive feel about scaled transistors. So it's worth our while to look at it for a bit. So now let's recall the gradual channel approximation. So here I have an NMOS with an inversion channel created. I have biased the source at 0. I have a high voltage on the gate, and I have a very low voltage that I've applied to the drain. So what we've seen is, because of that, a channel electron drifts from the source to the drain, right? And what does the gradual channel approximation say is that the change in the field along the y direction, that is along this source to drain direction, is negligible. So there's a very small field that is present on the electron as it drifts from source to drain, and it's relatively unchanged as a function of y, leading to the fact that you can separate the Poisson's equation into an x direction only, right? So in this case, if we look at the profile of the voltage along the channel, we see that the voltage profile along the channel starts with 0 and builds up to VDS, which is the drain to source voltage, in a linear fashion. So this is the outcome of the gradual channel approximation. This is what we used in the square law. Now what happens in reality is that as the electron moves from the source to the drain, you end up reducing the field in the x direction and increasing the field in the y direction, right? So in other words, you see that as I walk from the source to the drain, the increase in the voltage is not linear, but actually is pretty much non-linear near the drain. Right? And so in these cases, it's where the GCA breaks down. Right? So what you see here is that the electron close to the drain, and as we suppose we keep scaling the channel length or reducing the channel length, for much of its journey from the source to the drain, the electron is under very high lateral electric fields. Right? So when the electron is under very high lateral electric field, let's see what happens to the motion of the electron. So before, let's recall something about basic semiconductors. So suppose I have an electron in a semiconductor which is drifting in the influence of an electric field. Then if I plot the velocity of the electron as a function of its electric field, what we see that at very low electric fields, the velocity of the electron is proportional to the magnitude of the electric field, which means as I increase the electric field, the velocity increases in the same ratio. And this ratio was defined as mu, or the low field mobility of the electron or the carrier. Now in silicon, suppose now I increase the field that this electron is exposed to, what we see is beyond a certain field, the velocity of the electron does not keep rising. Rather, it saturates to a velocity, or the velocity is limited. So what we see here is that the velocity of a carrier in a silicon lattice is limited, and it's limited to a material quantity which is known as V subscript sat. So this V subscript sat is the saturation velocity, and that is normally modeled with what is known as an ESAT, or a saturation field. So what we say is we can break this graph into two regions, if you will. A low field region in which the velocity is proportional to the electric field, and in the high field region where for fields greater than saturation field, the velocity of the electron is constant and independent of the electric field. So what you see here is that when you are in this regime, that is when the electric fields are larger than the saturation electric fields, the velocity of the carrier, the velocity of the electron is independent. So no matter how much higher field I apply, I'm not going to change the speed of the electron or the current in the device. So what does it mean for the MOSFET IDS? So in the velocity saturated semiconductor, the velocity of electrons is limited to Vsat, and this is less than what is predicted by the low field mobility model, right? So if I were using the low field mobility model, so if I were using the low field mobility model to predict my MOSFET current, and in reality if the electrons were velocity saturated, what will end up happening is that my model will predict a current which is much larger than what is actually on the transistor. So because of velocity saturation, we expect the drive current to be less than what is predicted by the square law model. We expect that this difference gets worse at very high drain fields or when the transistor is in saturation. And we expect that when the gate length is very short, that is, suppose there is high field even in the linear region, then we expect saturation velocity to reduce the current in the linear region too. So a quick sidestep on the carrier mobility, or this term mu effective that we keep using in our models. So please remember, mu effective is a modeling parameter and it describes the mobility of an electron in a transistor configuration, right? So this is many times spoken of as the inversion carrier mobility. That is, what is the mobility of the electron in a particular semiconductor in an inversion region. And in most cases, we always see that the mobility of the carrier in the inversion channel is going to be much less than the bulk mobility. And there are multiple factors which govern this. It is related to the channel doping density, it's related to the surface roughness at this interface, and it is related to the charges or broken bonds that might be present either at the interface or within the first few layers of the dielectric. So which means that for us as a designer, this term mu effective is a technology dependent term. That is, mu effective is going to change for every generation and will change for every transistor type. So if you're looking at multi-VT devices which were created by changing the channel doping density, we should expect the mobility to change for these different transistors. The other thing we should also keep in mind is, remember that this electron, while it's drifting from source to drain, it is continuously under the influence of this field. And if you remember, we had discussed that the effective field of the electron is directed into the oxide. So the electron motion always ends up colliding with the surface, right? And now if I increase the gate field, that is if I create more charge, what happens is when I increase the gate field, I increase the probability of these collisions with the surface, which means that I will reduce the mobility. So in most cases what happens is, as I increase the gate voltage, while I keep increasing the gate charge, I might end up reducing the mobility, which means that it tempers the drive current that I might get out of this model. And this is normally modeled using what is known as a field dependent mobility, where mu effective is inversely proportional to this Vg minus Vt, right? So as your Vg increases, your charge in the channel increases, but it ends up reducing the mobility. Theta is a fitting parameter, so this is normally measured and then the model is fit to measurements. You also have a similar relationship to VSB, because VSB also changes the electric field that this electron sees in the channel. Now let's look at what happens to the current model if I include velocity saturation. So in the linear region, we know that IDS can be given as the inversion charge times the velocity of this inversion charge. If I invoke the charge equations from the previous lecture, IDS can be given by W Cox into Vg minus this expression, and that falls as a function of V of y into V. Now this term looks like the Vt of the device, right? So what you see here is Vg minus Vt, And this falls as you walk from the source towards the drain of the channel. Right? So I can write my IDS as WCox Vg minus Vt minus V of y. So this is the reduction in charge as I go from the source to drain. Now this velocity of the carriers, previously we had written it at just mu effective times Ey of y. Now we'll invoke the velocity saturation model, and so we write it as mu e divided by 1 plus Ey by E sat. So this is the model in velocity saturation, where Vt is the threshold voltage at the source. So you collect the terms and express E of y in terms of IDS and V of y, and E of y is nothing but the first derivative of voltage. And when you solve the equation, again similar to what we did in the GCA model, you get this expression for IDS. So let's look at that IDS a little bit closer. So if I look at the non-saturation region, without velocity saturation, my IDS is given by mu effective W by L Cox Vg minus Vt minus Vd by 2 into Vd. Now what happens with velocity saturation is that I have the same term as a prefactor that is tempered by this term, which is 1 plus Vd by Le sat. Now we'll come across this Le sat multiple times, right? So what is this telling you? That is that in case velocity saturation is important, then this term Vd divided by Le sat is critical, because that is going to reduce the effective current that is actually predicted by the square law. So when Vd is very close to 0, this term does not contribute, and in that case I'm going to have current very similar to the square law model. However, as I keep increasing Vd, I see that the current is going to fall much quicker than what would have happened in the square law model. So this term is the difference between the two. So let's talk about saturation. So now when we look at a transistor, for any given drain voltage, the maximum electric field always occurs at the drain. And carriers, when they are velocity saturated, cannot move faster than Vsat. So we define this Vd sat, or the drain voltage at which saturation sets, to be the point at which the drain field is equal to the saturation field. So this is slightly different from what we had seen in pinch off, because here the current saturates even before pinch off if the velocity of the carriers has already hit Vsat, right? And so beyond that point, the current will not increase. So I can talk about ID sat to be the value of current, what we've developed in the previous point, when Vd is equal to Vd sat, right? And so when I equate the two currents, and then I find an expression for Vsat in terms of Esat, right? Vsat is given by mu e by 2. What I get is an interesting expression. I get that Vd sat, or the drain voltage at which the transistor current saturates. So please note, I'm not calling it as pinch off. I'm calling this as the drain voltage at which the drain current saturates, is given not by Vg minus Vt, but by Vg minus Vt divided by this factor of Vg minus Vt by Le sat, right? And this term is a positive quantity, which means that this term is greater than 1. So when your device is velocity saturated, your drain voltage at which the transistor current saturates is not Vg minus Vt, but at some voltage less than Vg minus Vt. So the current saturates earlier in a velocity saturated device. The other point to note is that the ID sat is W Cox V sat into Vg minus Vt the whole square divided by this function. So what you see here is that it is no longer a square law, because you have this square function here, but you also have a linear function here. So again, here you see that ID sat gets tempered, right? And you see therefore that the Vg minus Vt square relationship is reduced, and you now have a factor which may be less than 2. To compare the two, let's think about the limits of velocity saturation. In long channel devices, I have this term Le sat. So whenever I want to evaluate whether I should apply velocity saturation or not, it's very useful to look at this expression, or this product of L times E sat. Now, if this L times E sat is much larger than Vg minus Vt, this indicates that the channel is a long channel device. There is no velocity saturation that's happening. And so my Vd sat is Vg minus Vt and my Id sat is given by the square law model. In short channel devices, what happens is as this L drops and this Vg doesn't drop as fast as L, eventually your Le sat becomes smaller than Vg minus Vt, in which case, in the most extreme case, if the device is completely velocity saturated, you see that the Vd sat is independent of Vg minus Vt, and you see that the Id sat loses its square function and actually becomes linear to Vg minus Vt. So if you look at a normal device, your normal device is going to lie somewhere between these two extremes, in which case your Id sat is not really a square law, but it's related to some power law. So sometimes we use power law expressions for very simple power performance modeling of circuits. So to conclude, the square law model is a great model to build intuition, but remember that it overestimates the current and the gate voltage dependence. The velocity saturation model tempers this behavior and makes it closer to the real MOSFET. However, the model still has a lot of assumptions. So especially as we work with FinFET nodes and GA nodes, etc., it's very important that we build accurate SPICE models. And once these accurate SPICE models are built, again, they are based off real silicon, we would use these to predict circuit behavior, right? And so that would be the best technique to do circuit level simulations.